Ever wondered how electrokinetic theory observations can predict the nature and direction of force during charging and discharging phases? Dive into the fascinating world of parallel plate capacitor impulse probes, such as those developed by Zinsser, Serrano, Campbell, and Norton AFB. The beauty of the electrokinetic field equation is that it doesn't suffer the handicap of certain other models. Why? Because it doesn't have a c-squared term in its denominator. This means it can predict significantly larger electrogravitic forces, but it's not as simple as it sounds. The current, usually designated as eosin at, and its derivative are both sinusoids. This necessitates a detailed analysis for each specific circuit and signal to determine the outcome. The intrigue of electrokinetic theory observations lies in their complexity and the need for precise calculation. So, the possibilities are vast, but a careful analysis is needed to truly harness the power of this theory. What if I told you that a quick change in current, like a surge or spark discharge, can produce the most dynamic electrokinetic force? Sounds electrifying, doesn't it? Well, it's not as simple as it sounds. You see, during a declining current surge, we face an opposing force until the current reverses direction. This can dampen the electrokinetic effect. But don't get disheartened just yet. The answer to this dilemma might lie in creative wave shaping. By shaping the waveform in a particular manner, we can potentially maximize the electrokinetic force. Imagine that. Now, some inventive minds have already started exploring this territory. They are using pulse power electric current generators to create propulsion. Yes, you heard that right, propulsion. This might sound like something out of a science fiction novel, but it's happening right now. It seems that with the right approach, we can turn a potential problem into a powerful solution. Now, let's not forget about the role of mass in our electrokinetic force equation. While the electrokinetic force theory offers intriguing predictions, it lacks one crucial element: the contribution of mass to the electrogravitic force. This omission is notable, especially when we consider the emphasis placed on mass by researchers like Saxel, Woodward, and Brown in their 1929 gravitator. But we're not without hope. Let's turn our attention to Takaaki Musha, a contributor to Electrogravitics 2. Musha offers a derived equation for electrogravitics that does indeed include a mass term. Rather than focusing solely on current changes, his model is based on the charge displacement, or in layman's terms, the deformation of the atom under the influence of a high-voltage field from a capacitor. His experimental results? Quite encouraging. Clearly, the role of mass can't be ignored if we want to fully understand and utilize the electrokinetic force. Finally, let's tackle a tricky question. Can we really create an unbalanced force that pushes against space? This idea might seem like a leap of faith. It's a concept that even seasoned scientists wrestle with. For instance, the author of the electrokinetic theory has grappled with this very concept in various domains over the years. Consider the homopolar generator. This device creates back torque that, ironically, pushes against nothing but space itself to implement the Lorentz force, slowing down the current-generating spinning disk. It's as if the generator is playing a cosmic game of tug-of-war with the universe itself, yet it works. This is the power and the challenge of electrokinetics. It nudges us to rethink our understanding of physical forces and the very fabric of space. It's as if we're on the brink of a new frontier, where our traditional concepts of force and motion are being challenged. It might be challenging to accept, but unbalanced force creation could open a new world of possibilities in electrokinetics.